Have to remind me to record because I started it already. All right. So, oh great. Now I can't connect. There we go. Lecture 5. Let's go ahead and get started. Let me draw a little plot over here. We got our x's and our y's, and we've got a whole bunch of data points, like so. Okay, and I have one extra data point right up here. Raise your hand. Do you guys think that that is an outlier? Yeah, okay, cool. How about now? Keep your hand raised. Yeah, still? How about now? Still an outlier? Still an outlier? How about now? Why not? Okay, and then how about here? Right, so similar to the very kind of first exercise where we were drawing lines through points, you guys have some kind of intuition about how, let's say, proper a line is, and in this case about what constitutes an outlier. And kind of in the same way that we talked about in that lecture, we want to think about this in an objective fashion, okay? And so you don't have to be like, oh, is that an outlier? Maybe, kind of, right? So it turns out there are like quantitative, specific quantitative measures that we can rely on to objectively decide whether or not something is an outlier. Okay, and again, I'm gonna kind of reiterate this throughout this piece of it. The classification of a data point as an outlier is one thing, right? And then the treatment of the outlier is another, right? And so right now we're just gonna focus on the identification of outliers, and then we can talk a little bit more philosophically about what you should do with outliers. So, outlier analysis. So this is a data point that differs statistically from other observations. Okay? So we're going to talk about two main ways that people typically measure the presence of an outlier. The first we're going to call leverage. So this is how much would predicted value change if the observation were shifted 1 unit in the y direction. So leverage is always between 0 and 1. And the way we write this, HII is equal to the change in predicted y over the change in the actual y. So let me not go too much into detail here, because actually I think the intuition behind what this actually looks like will become a little bit clearer when we do the example. I'm just gonna jump straight over to the second one, which we call influence. This you may also hear referred to as the Cook's distance. And this is the effect of deleting the point. So di is equal to the sum of j equals 1. So again, not something you have to memorize, but I will just kind of put it for your reference. This is a j, this is an I, squared divided by k times your mean squared error. And this item here refers to the fit without yi. So that's the fit that you would get by deleting the point. And k is the number of coefficients. Okay, so if we think about leverage and influence in the context of the regression, you may think about some kind of fit here that goes through here. Let's say we're thinking about this point, right? And if I were to move this point up or down a little bit, then that's going to shift this line up or down. And if I were to delete this point, right, that's going to shift the line in some way as well. And so essentially the idea is if I delete an outlier and my fit moves to a certain degree, then I would classify that as an outlier. And note that the leverage term, you're moving things up and down. So in some of these cases, the ability of the outlier to affect the fit can actually depend on where it's positioned along the x-axis, right? And so, think about like a seesaw, right? The farther you are from the kind of median of the points, the more influence you might have on the fit. And so that can show up in when something gets qualified as an outlier. So it's kind of an artifact of the way we decide to measure the outliers. Okay. Any questions or confusions about that so far? So let's just jump right into the examples and see how we can classify these guys in R. Yes.
Can we turn the light up on both of them?
Yeah, sure. Better? Okay. So, here we go. Hopefully you guys are all very familiar with this guy right at this point. We're going to do our usual hypothetical data points. Okay, so run. Here's our plot of x's and y's. And now what I'm going to do is I'm going to add a single outlier. So I'm going to redefine x by combining x plus one more point. It's going to be at 100, and y is going to be the y that I had before, and y will be 20. And if I now again plot x and y, I will now have some dude way out there in the ether that is going to be our example outlier. Okay, so example model 1, LMYX, and summary example model 1. So we know that the true value of the slope is about 0.5. And we know the true value of the intercept is about 0, right? That's the same. We're rehashing the same example that we've been doing over and over again. And let us now observe what adding this outlier has done to our estimates of the slope and the intercept. You know, this isn't to say whether the outlier is good or bad or anything. We're just seeing from, compared to the typical results, what a single point can do to our fit. Okay. So now we have a slope of about 0.4, so about 20% off. And then we now have an intercept of about 2.6, and it's statistically significant, right? And so the intercept has been shifted up and the slope has been kind of shifted down, which is kind of what you would expect, right? So instead of a line going like this, we now have a line that kind of goes like this a little bit to accommodate the fact that there's this point all the way out there. Okay, so hopefully nothing too surprising or unusual. And again, focused on identifying the outlier right now. We're not going to talk about what to do about outliers. So leverage example, the way that we calculate leverage, use this function called hat. It takes in a matrix, so we have to put our model into a matrix. And I can just straight up plot leverage, and I can plot x against leverage as well to identify which point is the outlier. So here, calculates the leverage, and then I plot it. Okay, and so, right, the leverage, basically, you take the original observation, and you shift that observation by some amount and see how your prediction for that value would change, right? And so for every single point you do that, and the one that's really high, this is the one that has what we call a lot of leverage, okay? And remember, leverage is always going to be between 0 and 1, and so there are like rough rules of thumb that people talk about. If you're above a certain, right? Because this is a very idealized data set, and so it's kind of easy to visually see. But there are some rules of thumb about the ratio between leverage values and high leverage values, or certain cutoffs that you might want to do. So like a cutoff for leverage values above 0.1, right? So this is, it's kind of funny because we talk about, that when I was showing the intuition and asking you guys, oh, is this an outlier? Is this an outlier? And then we're saying, okay, we can be a little bit more objective quantitatively about that. Yeah, and so the objectivity is like deciding a certain cutoff, which inherently is subjective, but still, it's something that at least people can agree on. And so you can say, I've chosen to classify a particular point as an outlier because its leverage is above X value. Okay? Any questions about that? Yeah, and you can plot it against X to see, to easily see on what X value the leverage corresponds to. And what do you guys notice about, even if I didn't have that outlier, what do you guys notice about the overall shape of the leverage values? Yeah.
The further on the outside or extremist and more the higher the line.
Yeah, and so this is that seesaw thing that I was talking about, right? So on the ends of your X spectrum range, just on average, you would tend to have an expectation that the leverage values would be a little bit higher. So that is one thing to keep in mind, that if you have a whole set of points that have higher leverage, part of that may be because of their position along the sort of spectrum of values, as opposed to them actually being outliers. Okay? Any questions or comments?
You're saying about the seesaw?
Yeah.
I don't really understand what you're saying.
Yeah. So if let me, maybe I can draw.
How I understood is on the ends of the X average range, there are more points, so there's more leverage.
No. Imagine that you have a bunch of points in your data, and almost the way that I might imagine this is that is that a good analogy? So on a seesaw, right, if you were to stand on one end of the seesaw, there's more torque, right? And so the closer you are to the middle, the less torque there is, in the seesaw. And so there's this analogous thing that happens that let's say your outlier is +3 above or something, or -3 below. It turns out that the influence on the leverage, if you were here or here +3, the influence of the guys on the end is bigger. Yeah, just by the fact that imagine drawing a fit line through these outliers one by one, and you'll find that the ones at the end cause that fit line to be more, it will change more in a very analogous way to this seesaw thing. And so one of the byproducts of that is that the leverage simply is larger for points at the end, on the ends. And I was kind of pointing out that you can actually see that very directly here, because I've now plotted the leverage against the x's, and you can see the ones on the end have larger leverage than the ones in the middle. Okay. Any other questions about leverage? So let's talk about influence. So Cook's distance example. It's literally a function called Cook's distance, and you just put the model in, and I can actually go ahead and just plot this to see what this looks like. And this, you end up getting a similar thing, right? So Cook's distance, what is the effect of deleting a point? Looks like this as well. And actually, I guess we could do something similar here. Let me see. I think this should work. Yeah. So with Cook's distance, you actually avoid that seesaw effect that I was talking about with leverage. You are not moving the point up and down, you are deleting that point. And so the behavior is a little bit different. And in this case, you would think about, so this isn't indexed to between 0 and 1, and here you would want to think about the ratio distance between your Cook's distances for your normal points versus your outliers. Yeah.
When you say deletes a point, is it deleting a random point in our data section, or is it?
The point that you are testing, whether or not it's an outlier, basically it removes that point and then runs the regression again, and then it checks how your fit essentially moves. Or it checks the sort of overall error. Yes?
Can you explain why, like, when you put leverage across axes, it's like a parabolic shape?
Yeah, so that's the seesaw thing that I was talking about. So the parabolic nature is the fact that points on the ends of your x ranges tend to have a larger influence on your leverage than points kind of in the middle.
Is it like a square relationship?
What the actual, if it's always parabolic, I think it is. Yeah, I'm not actually sure what the functional relationship looks like and if it's always the same, but yeah, the rough rule of thumb is that you on the ends they tend to be a little bit higher. Yeah. Yes.
Yeah, concern about the definition for outlier. Sometimes we see the box plot. Yes, they will mention, okay, the point is, outside the first quarter minus 1.5 into quantile range, this kind of definition. What's the difference between this?
Yeah. So the outliers that you see in box plots are a little bit less generalizable, I would say, because they are thinking about points in like one dimension. So you look at a distribution of the values and they call the outliers extreme values above and beyond certain quantiles, but like, or percentiles or quantiles. But in this case, we are looking at outliers in terms of relationship between multiple variables, right? And in this would not be a good example of the difference, if I wanted to think about a box plot distribution on x's because I selected the box plot to be 100. But imagine that instead I did, this. Let me rerun these guys. And let's say this is an outlier here, but then this is like 25. Okay. So here, the outlier is at point x25, y is 100. So in a box plot, if I'm to plot the distribution of x's, it would be, across this range, but you wouldn't actually observe that as an outlier because it's thinking about like a single variable. And this is like relationship between multiple variables. Let me just reverse this guy here. Okay, so yeah, that is kind of the standard way that people think about measuring whether or not something is an outlier. And so now let's talk a little bit about what you do with outliers, right? So I think that there is a very sort of common approach to outliers that people take, which is just to delete them. And I'm not saying necessarily that you shouldn't be doing that, but the treatment of outliers, constitutes probably a little bit more robust treatment than just deleting them, right? Because deleting them means something. If I were to, let's say I have 100 people and I want to take the average of the income, and one in 100 of those people is like a billionaire, right? And then if you take the average, maybe that really skews the income. And so I decide to drop it, and then I take the new average, and then you say, okay, the average of, the average income of the population is this new value, right? But really what you've done is you're actually saying not the average of that entire population, but the average of like a new subset of the population. And so anything that you do with an outlier, whether you choose to delete it or include it, there's inherent assumptions about that, about the population that you are now deciding to study and to include or not include, or sample not necessary population. And so what I would generally say is that you want to be robust with in the discussion of results as to what that applies to, whether or not you keep or discard an outlier. Does that make sense? Yeah, and I personally very rarely discard outliers. That is like part of the data. I think that they may be more influential on particular types of outcomes and predictions, but that if your sampling strategy is robust, then it is still representative of maybe a broader population, that there are naturally these outliers, right? So separate a little bit this idea of like what constitutes an outlier versus what you should do with an outlier. And I would say keep an open mind to not necessarily just deleting outliers when you encounter them, and think about what it means to either include them or to delete them in terms of like the interpretation of your results. Yeah. Any questions about that? yeah, so I'm not giving a like you should always do this type of answer for what to do with outliers. More kind of just like, think about it, use your common knowledge or common sense in working with these things. Okay. Let's continue onwards then. So the next topic that we will talk about now is multiple regression. So this is an extension of simple linear regression to predict the value of a variable based on the value of two or more other variables. Okay? And so a sort of very generic way, right? So we are now adding on to what we know about regression. So yi equals beta 0 plus beta 1 x1i. And instead of stopping here, I could add more variables, more explanatory variables to my equation. Okay? And in fact, I can write this generically to represent any number of variables, right? Something like this, yi equals beta 0 plus beta 1 x1i plus beta 2 x2i dot 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 up to plus beta n minus 1 xn minus 1 comma I plus beta n xn I and my error term. Okay? So, one of the reasons why I am pushing us to lean on some of the tools of interpretation as opposed to our intuition is because as we move to these systems that have more and more variables, it becomes harder and harder to kind of rely on our intuition. And so even something as simple as, something like this, we've seen many examples of this so far, and then we run a line through them. As soon as I enter something with more than one explanatory variable, maybe now I'm operating in 3 dimensions, right? And so we talked a little bit about what this looks like. So yeah, I'll kind of attempt to draw something in 3D. So the larger the point is, the closer it is to you, and the smaller it is, maybe the farther away it is from you. So if we have something like this, okay, and then the fit instead of a line would now be a plane that goes through all of these. So, it might be something that looks like this, right? A plane that extends in these directions. So it gets a little bit harder to visualize, And a lot of the things that we might rely on visually is going to get a lot harder. Okay, any questions about this so far? Okay, so let's jump over to R. And let's think about building on what we've learned so far to do multiple variable regressions. Okay. So I kind of like this example. It's a pretty cool demonstration of the power of the regression and also a caution on the use of visuals to identify things. Oh, sorry. There was one thing that I wanted to mention. I forgot to mention this when I was drawing the plots. So one kind of word of caution, if the number of parameters approaches the number of data points, you need to be careful. So imagine that you have 100 variables and 100 data points, right? It may seem like 100 data points is a lot to draw the relationships, but you have a lot of degrees of freedom, right? So this would be the equivalent of trying to, at a certain point, you have too many degrees of freedom relative to the number of data points. It would be the equivalent of trying to draw a line through a single data point, right, in 2D, or in 3D, trying to draw a plane through 2 points, and so on and so forth, right? And so that's one thing to be careful of is don't necessarily be deceived by the number of data points that you have if you have many parameters and degrees of freedom to operate on. Okay, so continuing on here, 100, 0, 50. And x4 is our unit 100, 0, 100. Okay, so we have 4 x's, error multi, so this is going to be our norm. Oops. 100, 0, 5. Okay, so I'm building a bunch of data, x1 through x4, and we're going to create a y multi. Oh my gosh, what am I doing? And that's going to be 0.5 times x1 plus 2 times x2 plus error multi. So again, this is like, imagine you have a big Excel data set, bunch of variables, and you want to understand the relationship between a particular variable and a whole set of other variables. You don't get to know this normally, but right, we're kind of playing God here. I get to decide what the true value of y is, which in this case is going to be half of x1 plus 2 times x2, right? It's not actually influenced by x3 and x4 at all. Okay, so I run all of these guys. Okay, and I'm going to plot all 4 of them, each variable against y. And let's see what that looks like. So par mf row equals c 2, 2. Plot x1 comma y dot multi. I'm just going to copy and paste this guy 4 times. And I'm going to change my x's to x1, x2, x3, x4. Okay. So let's plot this and let me, whoa. try this again. Error in plot. New figure margins are too large. RMF row. What am I doing wrong here?
Oh, for me it worked. Yeah, I got all 4 blocks in the server.
I've never seen this before. Plot.new figure margins are too large. Is this like a view thing? If I do this, does that do anything?
If you just try to do plot x1, does that pop up anything?
Yeah. What in the world would, all right, hang on. All right, I'm gonna give myself 1 minute to solve this. 1 second. Oh, interesting. Okay. So yeah. So apparently the resolution of this projection is too small. So I need to make the window larger. I've never had that problem before. Okay, so this is a word of caution about, again, just visual inspections of correlation between data. Okay, so what would we say about the relationship between x1 and y by looking at these plots? Sorry?
I mean, it looks like there is no relationship
Between x1?
Yeah.
What about x2?
there it looks like there is.
Yeah, right? And x3 and x4. Okay, what do we know about the true relationship between the x's and the y's? Yeah.
Well, x1 has a low relationship, but it's much like smaller than x2, and that's probably why it looks
Yeah.
like there's no relationship.
Yeah, right. And so this doesn't look any more related than this guy or this guy, right? And if I were putting in variables to test on the basis of a visual inspection between relationships of variables, I'd be like, okay, it's definitely x2. I'm just gonna put x2 in like, and you know, go from there, right? So this can be a useful exercise as a way to be inclusive of variables, but this is not a good exercise to be exclusive of variables to test, right? And so we're gonna talk about more robust strategies to do model selection. And so model selection refers to which variables I select to include as explanatory variables. And so not saying not to do this, because again, this can be helpful for inclusivity, but not for exclusivity. Okay, so let's jump back over. I wonder if it'll break it now. No. Let's run a regression testing all of the data. So we're going to do linear model of y.multi squiggly or tilde x1 plus x2 plus x3 plus x4. Run that and look at the summary.
What was the div?
Oh, so dev off is when you create a new plot window, or when you create a plot window, you can like close it manually, and that was a check for me to like if the error was coming from like an old plot. I just wanted to make sure that I was closing it. Yeah. So you don't actually, yeah, you don't need it. You don't need this. Okay, so let me run the summary of this guy, and let's take a look. Okay, so as far as the relationship between x1, x2, x3, x4, and y, we know the true values, right? It's 0.5 for x1 and 2 for x2, and then the other x3 and x4 shouldn't have a relationship. And we also know that the intercept is 0. So here, intercept negative 0.8, not statistically significant. And so we would basically say, yeah, this is 0, right? Good. 0.479, pretty close to 0.5. In fact, less than 1 standard error away from 0.5, and statistically significant, great. And x2, just about 2, statistically significant. Both x3 and x4 have some coefficient values here, but neither of them are statistically significant. And so the linear regression is able to bring us to our true values that we specified, right, on line 31, better than our intuition could by visual inspection. Okay? And, you know, these are the values that we would, yeah, hopefully expect to get out of the linear regression, and its ability to tell us, you know, the linear relationships, given that we do know that it's actually linear, right? So pretty powerful tool. In this case, we're kind of highlighting its ability to kind of ignore the noise and really hone in on the actual relationships in the data. Okay? And right, so pretty good R-squared values too, for what that's worth. Any questions? And again, this R-squared value is really kind of a product of the fact that most of the variation, you know, is captured in the x1, x2 variation relative to the size of the errors. But of course, you know, going back to my original point from that one lecture that R-squared isn't necessarily great indicator, the best indicator for all the good aspects of the model. If I were just to make the error 10 times as big and run it all again, run this regression, it makes it a little bit harder for it to hone in properly on the values, and the errors are forcing your R-squared to be smaller, but in fact, you know, if I look at the standard error of my coefficients, they're still kind of encompassing the true values So, you know, I wouldn't necessarily say that this model is totally bad. Okay, anyways. Any questions on that? All right, so moving on. One thing that I wanted to talk about this particular topic is kind of hard to cram in between a lot of other stuff. But interpretations of different forms of the linear regression. And so one of the common things that you'll see are transformations of your x and y variables in order to turn things linear, right? And so in a linear regression, you really want to apply linear regressions when relationships are linear, right? That's the best time, most intuitive time, right, to be applying a linear regression. And some people some people just use linear regressions for everything, but that's not necessarily going to be the best approach. So how often do we actually view data as being linear in the real world, in nature, right? And so sometimes, but actually it's much more common to actually observe things as exponentially exponentially distributed in your data. And because that's so common, one way that you can continue to use linear regressions, but with exponential data, is to linearize your data. And the way that you do that is to take the natural log, essentially, of your data, right? And so if you have data that looks in the tens, hundreds, thousands, tens of thousands, right, you can turn that exponential looking thing back into a line by taking the natural log. And that occurs with enough frequency that, you know, it's almost standard practice to essentially log things. And I want us to take a look at, kind of for ease of use, simple ways to help interpret that. Okay, so what are we talking about here? Let's take a look. So interpreting log x, where log is, so this is very important. Log is, every time I'm writing log, I'm talking about the natural log and not base 10. Because otherwise, the thing that I'm going to show you would not work. Okay, so when you don't log something, we call it, in the context of these transformations, like a level interpretation. So this is what we're used to. So y equals alpha plus beta x plus my error. I'm just writing alpha as the intercept, right? So alpha or beta 0. Okay. So if you run a regression and you get the results, the idea is if I wanted to interpret an outcome change from an input change, how would I do that? So who can help me out here? So if I change x by 1 unit, I would expect y to change by how much? Beta, exactly, right? So beta is the slope. So delta y is equal to beta times delta x. So x goes up by 1, y goes up by beta. Okay? Hopefully this all making sense, right? We've talked about this many times. Now, what happens if, how would you interpret this if a variable were actually transformed by log? In other words, you have an exponential sort of data set and you linearize it by taking the log, right? And so you would have ln, oh, this is called log dash level. So this would be ln y is equal to alpha plus beta x plus epsilon. So now, help me out here. If x goes up by 1, how would we interpret a change in y? Does anyone know? Any ideas? 1 over b. No.
2 times.
No?
E to the power?
Well, I'm kind of surprised no one's taken like an econ class where they teach you this. Okay, so or maybe you have heard of it, and I need to refresh memories here. But so this would be like if you were taking this in an econ class, they would tell you that the way you interpret this is like this. So if x goes up by 1, y goes up by 100 times beta percent. So x goes up by 1, y goes up by beta percent, essentially. Is that jogging anyone's memory? Has anyone heard of that before? So it's a kind of unique feature that allows you to do this interpretation. But really what they don't tell you in these econ classes, or maybe they do, maybe they give you like a little warning. So this is only for marginal changes. Okay, and the reason why I can simplify the interpretation this way is because the ln of 1.01 is approximately equal to 0.00995, or it's about 0.01. Okay. So if you are in the realm of dealing with log level, log, there's this handy little shortcut that lets you do these interpretations. So let's continue on and see what the analogy would be for doing something like this. So y is equal to alpha plus beta ln x plus epsilon. So now y is equal to beta over 100% delta x. So if x goes up by 1%, y goes up by beta over 100. And log would be ln of y is equal to alpha plus beta ln x plus epsilon. So this would be percent delta y is equal to beta percent delta x. So if x goes up by 1%, y goes up by beta percent. And the reason why this is really common in like econ, right? So if you're doing exponential against exponential, this like percent thing, if x goes up by 1%, y goes up by beta percent, that is the definition of an elasticity, right? And so structuring equations like this is a simplified way of denoting elasticity effects. And this is entirely an artifact of this relationship. And so this actually breaks down a little bit if you're talking about pretty large changes. Yeah, so this, again, I don't necessarily know how important this is to you guys, but you know, if you're dealing with logs of data, the basic idea again here is that, so we're all used to this intuition of x goes up by 1, beta goes, and then y goes up by beta. Instead of having to like do a bunch of math to like exponentiate and unexponentiate things to interpret the relationship between x and y, this is a shortcut that lets you say, roughly speaking, if I've like logged my y but not my x, then I change x by 1, then y goes up by beta percent, right? And then log, you know, if x goes up by 1%, y goes up by beta percent. It's just making the interpretation, it's a shortcut for making interpreting the results easier. Yeah, and so this is, you know, kind of for your reference, and so you also understand where this is coming from. And again, just you know, keep in mind this thing here, it's only for marginal changes. This is the reasoning for why we're allowed to do this shortcut, is this thing. Okay, any questions about that? All right. So moving on. So the next topic that we're going to spend a little bit of time here on are thinking about other types of variables. So there are these, so this is connected, right? In the log example, we're talking about a variable whose data contains data that's not necessarily linearly distributed, but exponentially distributed. There are other very common forms of data, which we'll call as dummy and categorical variables. Okay, so a dummy is a variable with only 1 or 0 to indicate outcomes. It doesn't have to be 1 or 0, right? It can be like heads or tails, true or false, whatever. But at the end of the day, it is something that has binary outcomes. And we typically will represent those outcomes as 0 or 1s when we do the actual sort of data processing and analysis. And so a dummy variable, so this is a special case of a categorical variable. So this is a variable that can take a number of discrete values, right? And so this might be something like education level. This might be something like political party, what department you're in. Okay. And what we're going to do is look at some examples of using these as explanatory variables and the sort of implications of doing so and what it means to interpret them. And actually, I'm going to put one more thing here. Oop, did not mean to use the eraser. One more thing here, which is an interaction variable, which is something we'll also take a look at. Little bit handier to think about it in the context of some of these guys. It'll make the interpretation of what an interaction variable a little bit easier when we're thinking of it with dummies or categoricals. But generically, this is 3 or more variables whose influence is not additive. So you might think of something like y equals beta 1 x1 plus beta 2 x2 plus beta 3 of x1 times x2. Okay. And in this case, the influence of x1 and x2 on y is not just additive, but the product of these two, which we call the interaction term, also has an influence on y. Is this a linear regression? Raise your hand if you think it's a linear regression still. Raise your hand if you think it's not a linear regression. Yeah, so this is still a linear regression. When we talk about linear regressions, it's about linearity in the parameters and not necessarily your input variables. And so beta 1, beta 2, beta 3 are linearly related to y, and that's really what we're referring to with a linear regression, okay? And so you can do all sorts of transformations on your x's, right? We did that, right? We literally took the log of the input variable, right, to actually turn it into, to linearize the data, right? But it's more about linear in parameters. Yeah?
For example, if the beta is a power number, is that a linear regression?
It depends.
Okay.
But generally no. Yeah, because then you would no longer be linear in parameters. Yeah.
Beta is a constant, right?
Yeah, except that if you have beta as a structurally related to other parameters in a way, you can make it not necessarily linear. Yeah, that's why I was kind of like, in some cases it can be, in some cases it can actually turn it to be non-linear. We're not really gonna get into some of these like weird exception cases, but yeah, it all depends on how the structure is set up. Okay, so let's look at an example. I'm actually going to be importing a data set to do this example, which you can find in the Canvas files. I've actually already uploaded it. And so if you want to follow along, just jump to Canvas really quick. There is a CSV called wages that I'm going to do for these examples. Okay, so to read a CSV, I use a function called read.csv. I need to talk about working directories for a second here. Okay. So there's a function called getWD, which stands for get working directory. The working directory is like where it's like the place that you're currently operating in on your computer. Okay, and so basically, so here, this is like my folder directory for where I am. And if you want to read in a file, you need to make sure that that file is in the working directory that you are currently working in. And if it's not, then you have to actually point to where that file is located on your computer. Okay. I'll help you guys kind of individually with that if you need. Right now, but not right now if you can't get it working. But yeah, hopefully this is kind of familiar to you guys. But anyways, so I'm gonna read in this file, and it is a data set called wages, and I'm gonna look at it using the structure function to see what is in here. Okay, so within this data set that I've loaded in, I have 1,379 observations across 6 variables, those 6 variables being earnings, right? And so this is the annual earnings of each observation being an individual. This is the height of each individual, the gender of each individual, the race of each individual, education, as in the number of years of education each individual has, and then the age of the individual. All right? Any questions about this? Okay. So let me just straight up go ahead and run a regression. I want to understand the influence of certain things on the person's wage, their earnings, right? So let's look at a couple things. Okay, so let me start with education. And let me do a summary of this wage model. All right. So somebody help me out here. Let's not necessarily focus too much right now on the quality of the model, and let's focus just on interpretation here. So I think this is the first regression that I'm running on, let's say, real data, not on like made up stuff, right? So now let's take a look at and see what this means. So we have an intercept, and then what we traditionally call as the slope. And so who can help me interpret these two? Yes.
Yeah, the higher the education is, the more you earn because the slope is positive.
Okay.
The intercept is negative, which probably means that it's not actually linear, I think, because it doesn't make sense that someone with no education like earns negative money.
Yeah. So I think your intuition is close. I wouldn't characterize it necessarily as not linear, right? But the fact that you are making predictions out of the bounds of what your data is trained on, and so does it really? Okay, no, I kind of see where you're going with the linearity thing, right? But you
Maybe
know.
inside of the bounds it's linear.
Yeah, exactly.
It's not like
Exactly.
general.
Yeah, so you know, if you're making predictions on places where you haven't trained, where there isn't a lot of data to train on, you might get some funky results, you know. And so, yeah, who knows? Maybe this is like real. Like if you have no schooling at all, maybe you're like you have negative earnings because you know you're like a drain on your parents or something.
Maybe, yeah.
No, but okay, great. And then so you mentioned the like positive part of this, and so kind of more specifically, what the regression is telling us, right, is that for every additional year of education that I receive, my annual earnings will increase by $4,490. Okay, so that's the sort of interpretation piece of it. Yeah.
Yeah, but also the R squared seems really low, so there's a lot of variation there that's not explained very well.
Yeah. So again, I'm kind of mentioning that I'm not focused on like the quality of the model yet. So we're just thinking about interpretation, and so we're gonna expand on here a little bit, and then eventually talk a little bit about doing some model quality checks. But okay, let me modify this and include education and age as well. And let's run this and see what happens. Okay, so just as a reminder, the old one, 4490. And then our intercept is even lower now, but we actually have this new thing here. So for every year of education that I receive, my income goes up by $4,692 as opposed to $4,490. And for every year in age I am older, I get $240. On average, you would see that the annual income of the person is $240 higher. Okay? So now we are dealing with a multiple regression where there are two different things that influence my income, right? It's that my age influences my income, as well as the amount of education that I have influences my income. And you can continue to layer in things that you might imagine affect your income. So now we're going to add in gender. Okay. And so because the gender variable is not like a continuous variable, it is a discrete variable. In this case, it is a dummy variable, as we just discussed. Yeah, you can't be like, here, do the math for data that's, you know, numbers, and then like male, female. You don't know how to do that, right? And so remember I mentioned that treating a variable as a factor turns it into essentially these like ones and zeros for columns. So you can imagine that now instead I'm running a regression on a column of zeros and ones that are indicating whether or not you are male or female. Okay? So let me run this and then let's talk about the interpretation. Okay. So education and age, kind of similar in number, $4,470 for every year of education, and for age, $200 $81 for every year and age that you are. Okay, but now we've layered on an extra variable that is different from how we've traditionally been interpreting these guys. Okay, so yeah, so if this is your first time dealing with dummy and categorical variables, this can be a little bit confusing, but generally we think of dummies and categoricals kind of as essentially another intercept, okay? One thing that you'll notice is that there's two genders, you have male and female, but in the results, we only see male. And so why is that? The reason is because the information about one of the default values in a categorical variable will always be captured inside of the intercept. And so you can really think of this intercept as what it would be if you were female, okay? So for simplicity's sake, I know that we talked about that it's a little bit ridiculous, but let's say you are 0 years old and you have no education. How much would your expected income be as a male? Who can help me out here? Anyone?
Minus 26.
Yeah, right, okay. Were you about to say something?
Oh, no, like minus 26 or something.
Yeah, and so where did you get the minus 26 from?
The intercept of the whole model.
Yep.
Plus the 1 or 0 factor.
This thing, yeah. So basically it's saying if you were female at 0 years of age and 0 years of education, you would make negative $48,000. And if you were male, then you would make negative 48 plus 21, so negative 26. Okay. Yes, also an indicator of some kind of gender bias in society, right? But yeah, so let's say that you are 20 years old with 10 years of education. So 20 times 280, that's what, 5,600. 10 years of education, 44,000. So 5.6 thousand plus 44,000. So about 50K. So at 20 years old with 10 years of education, you'd make 50K. And if you were a female, starting out minus this, and so you would start out at maybe 2,000 a year, and then if male, plus another 21,000. So if you were to make that prediction based off of these values, female, 20 years old, 10 years of education would make roughly 2,000 a year, and a male would make roughly 23,000 a year. Yes?
I have a question. What would happen, or like how would this look if the factor also influences slope? Would I have to add the interaction term we had before? Or?
Yeah, I'm going to talk about that in a bit. Yeah.
So like the male and female are like extreme.
Mhm.
They're not like 1 and 2. So how does one know like?
Yeah, so that's why I did this factor thing. So factor is the way that you transform these like strings or characters into like a digestible variable that the regression can handle.
I have noticed that why default as female and why male as male?
Yep, great question. So if you remember back to week 1, when you change something as a factor, you have levels, right? And so the variable that gets dropped and inserted as the intercept is always the first level in the factor. And that's the thing that causes, that is the thing that causes this to show up as male and the female being dropped. And if you remember back when I was saying that the selection of which character is selected as the first level is alphabetical. So F comes before M, and therefore it looks like this. Okay, actually, so let me ask you guys something. Let me show you guys how to make female as the one that appears here and male as the one that gets dropped. And that's just changing the levels. But before I do that, what would the values be? What would the new value of my intercept be, and what would the new value of the female one be? Would it be flipped? Yeah.
So the intercept should be the minus 26,000, and then the factor would be a negative number, so the difference would add it back.
Yep, exactly. So this in here, we would expect that to be negative 26,000, and it would be, for female, it would be negative 21,000, right? So let's see if that's correct. All I have to do here is go into sex, and I'll go levels equals C male comma female. So I've swapped the order manually, because by default it'll put female first. I do this. We suddenly see exactly what we predicted. The intercept is now negative 26,000, and the female is negative 21,000. Okay? Okay, let me get rid of this stuff real quick. Go back to here. Okay, goodness of the model. Let me run through a couple things very quickly. We saw the diagnostics in terms of the R squared and the statistical significance of things. One thing that I'll always recommend is to look at the residuals. Oh, shoot, I'm still in the part thing. Dubbed off. And all right. What do you guys think about these residuals? Yeah.
Like the higher values, I'm overestimating them, I think.
Yeah, so possibly. And then there's also this line thing. Is that random? No. So there's some problems happening here. And so I think more residuals that you look at, you'll be able to sort of quickly identify certain things. And so I'll just, some things that come to mind to maybe fix is for the large value thing, maybe if I do the log of the earnings, I might have a better chance. Education, age, factor, SMAX. Data equals wages. There's some data points that were dropped, which is fine. Maybe those people had no wages, right? I can look at the summary. These should look pretty different now. And so remember the way that we interpret this. For every year for every year of education that you receive, we would expect your income to increase by 16%, right? Now we're talking about the log level thing. For every year in age, your income would be about 1% higher. If you're male, you would expect to make, on average, 100% more income than a female, so double the female income. It's real data too, so yeah, definitely not great. Okay, let's look at wage model log. The residuals again. Okay, we're looking better here. So this part looks good, and then I got some weird crap going on over here. And typically this means you've got a bunch of data. Oh, yeah.
When I tried to do the log variant, I got errors produced.
Yep. So what's the log of 0? Yeah, non-existent. Yeah, so what the regression does is it doesn't know how to deal with this, and so it just drops those points. So yeah. Yeah, exactly. No. I think that, like, in this case, yeah, actually, so okay, good question. You know, I talked about when you should be dropping points. In this case, it's like, it's dropping people who have a wage of 0. And so your interpretation of the results now changes. Instead of saying across the population what the average wage is or whatever, I'm now saying, you know, what are the characteristics of these relationships for people who have a wage, right? And that is now the new way I should be speaking of this data. Yeah. Okay, and so I'm gonna fix this. I kind of played around with this. I know kind of what's causing this. Oftentimes you have a bunch of values that are kind of clustered in some of extreme ends that makes this kind of line happening. And so you can actually fix this by doing a further filter with wages where they're more than $1,500 a year. You know, these are often, like babysitter type jobs, like really sort of temporary wage earners. So I'm excluding that, and if I do this, then your residuals actually look clean, right? And so here, I would say this is a really nice, realistic plot. Or this is a nice plot of residuals coming from kind of real data. It's like, yeah, maybe there's some skew towards the negative, right? Which means that the relationship is maybe somewhat biased, but it's a lot better than it was before. And we're, for class examples, we're not aiming for perfection here. And these are kind of the new values, right? Every year, 12% increase. Every year of education, 12% increase in wages, almost a 1% increase per year of age, and then now by removing a lot of that stuff, we're actually saying males make 45% more than females. Okay? Any questions about that? Okay. Let's do. So this is more for the purposes of understanding the interpretations. And well, I guess I'll just keep this little filter thing on here. And actually, let me type this first. Unique wages dollar race. So in the data set, there's 4 races being represented: white, other, Hispanic, and black. Okay? When I run this, which race will be dropped and why? Yes, because it's alphabetical. Okay? And if we wanted to change that, we know how, right? You would specify in the levels for the factor, and it'll always drop the first one. Okay, so let's run this, and now let's do the interpretation. Okay, so this is just races. We have an intercept, Hispanic, other, and white. So, who wants to help me out here and help me interpret these coefficients? In the back.
They're all relative to, basically how much more you make relative to someone who's
Yep. And so someone who would be black in the data set, we would expect them on average to have wages of $31,813, and everything, right, is relative to that. So you're saying, so someone who's Hispanic would make 29,600-ish, right? Someone of an other race besides that would make 37,300-ish, and then if you were white, you would make 38,600-ish more, right? So you just add these guys in, so these are sort of directly comparable, and so the intercept and then modifiers for the intercept based on the values here. Let's look at the standard errors and what they mean, right? And so the intercept is saying it's statistically significant. And so if you, in the data set, if you're black, you're definitely not making 0, right? You're making some amount of money. But then for these guys, these are modifiers of the intercept, and so are you statistically different from this? You know, and since these two are not, they're saying, yes, we may observe higher or lower on average compared to our baseline race, but these just as well could be 0 some amount of the time, and therefore these values, you know, you could say Hispanic and other are not likely to be making different amounts of money from someone who is black. But in the case that you are white, it is statistically significant at the 5% level, and so you would say, but I am sort of statistically confident that if you're white, you would be making more money than the baseline race, okay? So everything is in relative to the intercept. And so I want to, and so you can also, like I said, the default is just based on the level of the factor, and so you can re-level it if you wanted to, wages, dollar race, reference equals white, and so that would make If I copy and paste these guys again and just run these after releveling, you should see, oops. Wait, what did I do?
Is it wages or wage?
I think it's wages. Why did that used to work?
That was wage.
Huh. Oh. You know, I bet it's because with read CSV, it's no longer read in as a factor. Okay, so is- yeah. Okay, and so if you make white the baseline, then you start at that higher value that I was mentioning, and then everyone else ends up being negative. And they would be statistically different. And you actually get slightly different data here, right? Because you're testing against a different reference baseline value. And so the statistical significance stuff might actually differ when you have a different baseline. So let's see. This can be a little bit confusing for folks who are seeing this for the first time. And so I wanted to kind of end today talking about a visual way that I think maybe might help clarify some of the interpretation. And so let me kind of do that quickly here. So let's consider the case where I have wage is equal to beta times gender, and that's it. And so in a model that depends only on gender, would I expect the wages to change as my education changes? No, right? And so you would just have two genders here, and so you might have like male, and then you might have female, something like this, right? And so just qualitatively from the data, it was showing males have higher, females have lower, and so you have essentially two intercepts where this is your default intercept, and then the other one is the beta value plus the default intercept. Okay. Okay, and so what if I had wage as just beta times education? And so in that case, we would see wage, education, and we would just see a line, right? And that positive line, that slope is just, for every year of education I receive, I get some beta amount of extra income. And then we explored the model where wage is equal to beta 1 gender plus beta 2 wage. And in that case, the way that this looks. Sorry?
You mean
Oh, sorry, yes. Then you have two lines here, male, female. Right, we saw that the education, every year of education was influencing the income the same between males and females, right? And so that means that the slope of these two lines is the same, but now we have two intercepts, this being the baseline, and then that difference being the beta for males. Okay? And then the one that I didn't show would be the case of what if I wanted different slopes for each of the genders as it pertains to education. So the question is, does the impact of education on income, is that different between genders? And in that case, you would have two different slopes, right? So wage is equal to beta 1 gender plus beta 2 education plus beta 3 gender times education. And we can see that like so, wage, education, and you might see something like male and female. Okay, and so in this case, the interaction allows you to have different slopes. Any questions about that? All right, I think we have just enough time to maybe run that to show you what that looks like. Wage model interaction, so that'll be LM. Let's do log earnings, or no, I'm just gonna leave it as earnings. Earnings on education plus factor sex plus oh, how do I do this again? Is it colon or just, I think I can just do times, right? Data equals wages. We'll see if this works. Okay, summary, wage model interaction. Yeah, okay, so real quickly, now I have the baseline here, starting at negative 22,380 as a female. Every year of education for both males and females, they'll both receive 3522 additional dollars for every year of education that they get. But if you're a male, you also will get an additional 1815.7. So the female slope is 3,500, and the male slope is 5,300, right? And so now you have two different slopes because you're adding these guys up, and then it actually will lower the intercept for males a little bit. Okay. Yeah, so that's a quick run through of practical example showing dummy and categorical variables. Some of you guys, I'm sure, have seen this before. For those that this is maybe a little more unfamiliar, a little newer, make sure that you get a good sort of grasp of the intuition in interpreting these. Very helpful to understand and be able to interpret models that have these, which are very common, right? And so I'm sure you guys are working through some of these there. On the next homework, we're gonna do some interpretations of these types of things as a way to help solidify these concepts. Okay, great. That's it for today, and I'll see you guys on Wednesday.